We're going to finish up now with a few problems that are applications of what we've been doing. The first one's problem number 58. Again, 58 and 59 look at using the right-hand rule properly. Okay, in order to do that, you take your hand. Now, in the case of these different examples, your fingers are the field, and your thumb is the direction of the current. And you have to remember that by convention, and don't ask me to explain this because I don't know how they did this or came up with this, but they decided that the current is in the opposite direction of what they show as the electron velocity. And so, for example, in B, it shows velocity is up, which means the current is down. It's the direction of the positive charges. So for the first one, if you point your thumb in the direction of up, then on the right side, it moves into the page, and on the left side, it comes out of the page. So on the right, it moves into the page, and on the left, it comes out of the page. The second one, because it says velocity, it's the opposite. So on the second one, on the right side, it's out, and on the left, it's into. And then the last one is the same as, C is the same as B, which means it's out on the right and into on the left. Now that's strictly because of convention, okay? Now when you do number 59, you take your fingers and point them in the direction of the current. So the first, on A, you're holding your hand in front of you and making a backward C, and the thumb is coming out at you. And so that means that the current or the field is out of the page as a result of that current that's shown. The second one, you have to kind of turn your hand backwards because your fingers should be pointing right at you, which means your thumb is directed to the right. And then C is the opposite, so your thumb is directed to the left. So the first one is to the right, and the last one is to the left. Hopefully that makes sense. Number 63. Number 63 states, non-nuclear submarines use batteries for power when submerged. A, find the magnetic field 50 centimeters from a straight wire carrying 1200 amps from the batteries to drive the mechanism of the submarine. So the field is going to equal this mu zero times the current divided by 2 pi times the distance that you're talking about. In this case, the distance is 50 centimeters or 0.5 meters. So if you put mu zero, which is 4 pi times 10 to the minus 7, times the amperage, which is 1200, divided by 2 pi times r, which is 0.5 meters, and you do the math here and you get 4.8 times 10 to the minus 4 Teslas of field. B, that's A, B states that what is the field if the wires to and from the drive mechanism are side by side? Well, if it's to and from and they're side by side, it's going to be zero because there's no net current that's generated. C, if the wires don't cancel, it says discuss the effects this would have on a compass if it's not shielded. If the amperage does not cancel and it's not shielded, then this Tesla, this magnetic field, would have an impact on the compass and cause it to misread. Number 67. Number 67 states the following. Measurements affect the system being measured, such as the current loop in figure 2256. Estimate the field the loop creates by calculating the field at the center of the loop 20 centimeters in diameter, carrying 5 amps. Okay. So the field is equal to mu 0 I over 2 times R. Not 2 pi in this case, but 2 times R. And this, so you have 4 pi times 10 to the minus 7 times 5 amps divided by 2 times 0.100. And if you do the math here, you get 3.14 times 10 to the minus 5 Tesla. The second question is, what is the smallest field strength this loop can be used to measure if the field must alter the measurement field by less than 0.01? You just divide this by 0.01 percentage points. Percentage is 10 to the minus 2, so if you do that, you get 0.314 Tesla. And that is the last problem.